So the idea of lecture 1 and lecture 2 will now be used in the discussion of correlation functions. In the next lecture tomorrow, I'll talk about using some of these correlation functions to actually understand the properties of the quadron plasma. So I don't have to publicize it, Philippe has done it for me. Thank you very much. If you think in terms of correlation function, it's a very broad term, and this slide is meant to illustrate that in measurements of correlation in particle physics, nuclear physics, and particularly in heavy ion physics, there are many, many types of correlation we can measure and study. At the end of the day, all these correlation functions are built on the same thing. They're built on n particle densities, and depending on how you integrate or don't integrate or marginalize these correlation functions, you will have what I call integral correlators or differential correlators, and I will give you examples of some of that in the presentation. It's obviously impossible for me to cover all of this, and I don't think it's desirable either. So some of the topics I might be covering, I have included a lot of things in the presentation. I'm not going to cover everything, but the very basic is what is a correlation function, and we can introduce the notion of correlation function on the basis of covariance that we talked about yesterday. Then we can give a full definition of what correlation functions are. And then we can split into integral and differential correlation functions. And then why measure such correlation functions, and talk about some examples, and perhaps some technical details if that's of interest. So what is a correlation function? One way to introduce the notion of correlation function is to proceed by an extension of the notion of covariance. The covariance is based on two observable, x, y, and you consider how they co-vary when there are fluctuations. And so I will introduce the notion of covariance in the context of two particle measurements, of cross-section measurements. It can be formulated in a more general way based on cumulants and generator functions, moment generating functions. And in the concept of course, of correlation function is not limited to particle physics or nuclear physics. It's a concept that you can use in many other fields, but I will restrict my discussion to nuclear and particle physics. Okay. So let's set up the problem in a simple way. Let's suppose that we're measuring some collisions. And so there's a collision happening here, let's say lead on lead or proton on proton at some fixed energy. And out of this collision are two particles, or many particles are coming out, but I'm going to focus on two of the many particles that are produced. And I'm going to ask myself, are these two particles correlated in any way? And so let's fix the solid angle of these two particles. So that means the polar and azimuth of these particles. I'm going to call that omega 1 and omega 2. And so these particles will be at some momentum, P1 and P2, and you can translate that in terms of pseudo-rapidity and transverse momentum, but that's a detail. Now, given that we're dealing with collisions, nuclear collisions are intrinsically stochastic phenomena. It's like radioactive decay. If you look at the same point in space, you will see the number of particles fluctuating one collision after the other, because that's the very nature of what these things are. And so discussing anything event by event is essentially very difficult or impossible. So we're going to be dealing with averages. And so on the previous slide, I had two solid angles, omega 1 and omega 2. In each of these solid angles, I'm going to consider the average momentum, the average number of particles that are produced over a large data set, a large set of collision ensemble. What is the average multiplicity or number of particles in these two solid angles? And so this average number, it turns out, corresponds to a cross-section. It corresponds to the integral of the cross-section. So this is the cross-section. Well, in some Garden form. So this is the number of particles emitted as a function of pt, phi, and eta in the solid angle, and we integrate over the solid angle. And that gives us an average number of particles in that solid angle. Of course, I could also look at how I could try to characterize how the number of particles in each of these solid angles is fluctuating. So I would calculate the variance of that number in the given solid angle, and that's the average of the second moment minus the square of the first moment. So that's certainly one thing one can do, how much it fluctuates in a given solid angle. But we can also, and we learn more from this, we can correlate the multiplicity in the two solid angles. So that would be the covariance between the number of particles in the first and the second solid angle. And so obviously, as you know from prior discussions, this would be the average, the expectation value or average of the product of the two minus the average, the product of the averages. Obviously, this is an experimental driven quantity as much as physics driven. If I use a very small solid angle, these multiplicities will be small. If I use a very large solid angle, I will integrate a larger fraction of the total cross-section. And so there's something experimental in here that we will try to get rid of in a moment. But before we get there, I just want to remind you that when I look at a covariance like this, I can have the situation illustrated here. A, B, and C, the covariance is 0 because there are fluctuations, but obviously X and Y, which would be represented by N1 and N2, I didn't change the scales here, the axes. So N1 and N2 here would be uncorrelated. They would also be uncorrelated here because N1 would fluctuate a lot, but N2 less, but there would be no special dependency of one to the other. In this case, if in a situation like this, it would tell us that when N1 is increasing, so would be N2. In this situation, it would tell us that if N1 is increasing, then N2 would be decreasing. Right? And so if I was then just focusing on those two solid angles and making such a plot, I could see what's happening at that particular location, pair of location in space. In momentum space. So that was my setup. Now what we're going to do is describe these correlation functions in terms of pseudo-rapidity, the angle, the azimuth angle of the emission, and so on, and the PT of the particles. So now here I have two plots. So let's fix for now at the omega 1 and omega 2. So I have the number at omega 1, which is eta 1 here, the number at omega 2, which is eta 2 here. And what I've simulated, this is a simulation, I've simulated a positive correlation. Okay? This is at a specific set of, or pair of solid angles. In general, with a large detector like the Alice detector or the CMS detector, now you can look at many different combinations of solid angles. And so then you can make a plot like this one where now each bin in this, along this axis and that axis, will be a pair of solid angles. So this point here will correspond to a large eta 1 and a small or negative eta 2. And so you can consider that in each bin here, I have studied this covariance and I'm plotting the covariance. And so what you have to consider then is the vertical axis, or outside of the page axis, the magnitude out of the page is telling us the magnitude of the correlation here. Okay? Now, as I already said, if I only look at this part obviously is dependent on the size of the detection cell that I'm using, the solid angle that I'm considering. So to make that somewhat independent of the solid angle, I can divide by the solid angle. So I'm doing a two-particle correlation. I'm going to divide by the solid angle of the first and the second particle. If I do binning that is uniform in eta and phi, this factor will be the same for all the possible combinations. Okay? So in practice, that's what we do experimentally, because that's the only thing we can do. And so, at the end of the day, we are going to be considering two types of quantities. What I will call single particle multiplicities. So that's the number of particles on average at a given momentum. And you will recall the discussion from yesterday, where I said, well, this is what I have here. This is a two-dimensional histogram. In each bin, I'm measuring the number of counts, number of pairs at a given eta 1, eta 2. I analyze all the data from a given run that led at 2.76, and I divide the number of counts in each bin by the number of events I've looked at, and that gives me these numbers. Right? And so what that corresponds to at the end of the day is an average number of counts of single particle at a given momentum. And if I divide by omega, now I'm dividing by the bin size, and I can use that now as an estimator of the density. Okay, that was the point of the discussion yesterday. So this is an estimator because I'm doing this over a finite size bin for a finite number of events. In the limit where I go to an infinite number of events, I would have perfect statistics. And in the limit of this solid angle being 0, then I would get the true density produced by nature. All right, so this would then correspond to the density of single particle at a given momentum. Likewise, if I now take the number of pairs at P1 and P2, divide by the solid angle, I have an estimator of the two-particle density at P1, P2. It's an estimator. It's an estimator again because I have finite statistics and I have finite solid angles. In the limit where the solid angle would be 0 and an infinite number of events, I can write it this way formally. This then becomes a density, the true density of particles produced at this P1 and P2. So, having these densities, then I can introduce a correlator, C, as the difference between rho 2 and the product of rho 1 and rho 1. Now, by construction, at each value of P1, P2, for a specific value of P1, P2, this behaves like a covariance. But I can now, because I have a large data set, I can look at different combinations of P1 and P2, and now this covariance will take different values. So effectively, this becomes a covariance that is function of P1 and P2. And it's defined formally in the small solid angle limit, 0, and non-infinite number of events. And that formally defines what a correlation function for two particle, what it is. Now, with this expression here, I obviously have possible dependence of P1, X, Y, and Z, so 3 coordinates, likewise for P2. And so in principle, what I have here is a 6-dimensional object. I have a quantity that lives in 6-dimension space. And of course, we never look at such quantities, or rarely look at such quantity, because A, we don't have typically very much statistics or enough statistics. And I don't know about you, but it's very hard for me to visualize anything in 6 dimension. And so what we tend to do is project these 6 dimension onto lesser dimension spaces. And we do this with specific ideas in mind on what it is we try to understand or what phenomenon we're trying to identify. So in principle, when we do these projections, we can use Cartesian coordinates, rapidity coordinates, pseudo-rapidity coordinates, and so on and so forth. And so there's plenty of choice. In practice, what's been done in the heavy ion community at RIC and the Large Hadron Collider is to use eta and phi, eta being the pseudo-rapidity, phi is the azimuth angle, and pt, for so-called unidentified hadron, that is charged hadrons, or even neutral hadrons. And when we can actually identify the hadrons based on specific energy loss, time of flight, or what have you, then it's more convenient to use the rapidity themselves, because physically that's what is more meaningful. So we have 6 dimension. It's too complicated, so we're going to implicitly do some averaging, which the statisticians call marginalization. And so we're going to project this and average the 6-dimensional space onto just a few coordinates. The first measurements of the correlation that were done at RIC and that were very successful were projecting on the so-called delta phi axis, delta phi being the difference of the azimuth of the particles of a pair. Then there were plots on delta eta being the difference between the rapidity of the 2 particles, and eventually, with enough statistics, people were able to do a correlation function involving both axes. And then, with time going on, people have done more and more sophisticated things. Let me give you an example of one of the most famous plot out of the RIC program, which was called jet quenching discovery. And so what is shown here, it's actually not a real correlation function. I'm cheating a little bit, but what is actually shown is a cross-section as a function of delta phi divided by the number of high pt particles. So what's actually shown here, so it's you have a measurement involving 2 particles, and I don't remember, I think this was 2 to 4 GeV over C, the first particle, and the second particle was in 0.2 to, I believe, if I remember serves me well, it would be 1 or maybe it would be 2, but the point being that you have a so-called hard particle, a high PT particle, quote unquote, and a low PT particle. So in the transverse plane, the collision happening here, now you can have one particle 1, at some angle phi 1, and you can have particle 2 at some angle phi 2. And the angle that is being shown here, delta phi, is the difference between these 2 angles. So that would be this angle here. So what is the meaning of this? If I have a jet, so jets are the products of hadronization. We have a hard collision, 2 partons. Let's say you have a pp collision. You have 2 partons colliding. They scatter with a very high momentum. Those partons then would like to escape the system in which they live, but as they do, they have to hadronize. This hadronization process leads to a production of many hadrons. And typically, what you will see is that you will have one parton going this way, and this would lead to particle production in a cone. And so this would lead to many particles in the cone. And so that will be the first jet. And then you will have, by virtue of momentum conservation, you will have back to back with this, you will have another jet, jet number 2, with many particles of its own. Now, if I say, okay, this is the z-axis, now I look at the phi axis this way, right? And so that jet is on average at 180 degrees from the first jet. And so that means pi here. And so now in this jet, I have several particles. Those particles are close to one another. And because they're close to one another, delta phi is relatively small. And so this peak here corresponds to pairs of particles that are in one of the two jets. Whereas this second peak corresponds to particles that are emitted one in one jet, one in the other jet. And because, well, the jets, the partons that are emitted are back to back, essentially in phi, but the particles that are inside the jet, as a byproduct of the fragmentation of the jet, they are scattered relative to the axis of the jet. So the peak on the OA side is somewhat broad. Because on here you have all the particles within the same jet, and here you have particles belonging to two jets, and they have scattering of their own. And so this peak is broader. So that explains the logistics, so to speak, of the plot. So what is actually shown here? So you have 3 data sets. You have the reference, which is the solid histogram, solid bar, solid line in black, which has one nice peak at 0, which we call the near side, because the two particles are near one another. And then you have another peak, very large as well, on what we call the OA side, because one particle is pointing away from the first one. And so in the PP, you see a nice peak both on the near side and on the OA side. The same is true essentially in D gold. Right? D gold is shown with red dots. You see again a peak and another peak. So, okay, in D gold you have a small system, small nucleus hitting a big nucleus, and you still see basically these two objects, these two jets. Now, in gold, what you find is there's a near side peak and essentially nothing on the OA side. And so this was considered the discovery of quenching of the jet. And so when we try to visualize this, you can say, okay, this is the two nuclei that are colliding with one another. One is coming out of the page, maybe this one, and the other is going into the page. And so now I have a region of overlap. And in this region of overlap, you can have partons carrying a large fraction of their proton, momentum of their proton, they're going to collide. So let's say I have one here, such collision. If a jet is emitted this way, this jet then has very little medium to cross, and therefore is unlikely to be affected by the presence of the medium. If, on the other hand, the other jet going this way now has all this medium to go across, and as it goes through the medium, it will interact with the medium and can lose energy. And then as it loses energy, the cross-section that you measure on the OA side will be suppressed, and that leads to the disappearance, or apparent disappearance of the OA side. This was done a little more complicated. As you can tell here, when I have an overlap, there is an axis. Along this axis, the system is long. Along this axis, the system is smaller. And so if you have emission along this direction, then you have a smaller system to go through. There should be less attenuation, and that's what you see. You see still a little bit of a peak here. Whereas in the out of plane being this direction, right, there's more system to go through on average, therefore there's more attenuation, and so that's what we see in the red points. So this was the first use of correlation function at RIC, and then ever since many more plots like this have been made. From an experimental standpoint, this was done with so-called trigger correlations, where you take the cross-section, you divide by the number of particles. It's not strictly speaking a correlation function. I cheated a little bit. What I didn't tell you is that in PP, what is shown is what we measured. What is shown here for lead actually rides, there's a huge combinatorial background here, pairs emitted in all directions. There's huge combinatorial background that has been subtracted to make this plot. And so strictly speaking, this is cheating a little bit. It's not a real correlation function, but I think the message was pretty clear. When you measure correlation function P1, P2 with this correlator, what you find is that this is now behaving like a covariance, therefore it can be positive, null, or negative. Whereas the per trigger quantity that I was showing you in a moment ago can only be positive. Now, there are merits and advantages and disadvantages of doing one or the other analysis. If you do this type of analysis using true correlation function, you can identify regime of or regions of phase space where you have true anti-correlation or true correlation in the sense that the covariance is positive or negative. Okay, and if you have regions where the two particle density is essentially equal to the product of single particle density, then you have zero covariance, therefore the correlation fraction vanishes, and you can claim then that you have true statistical independence or Poisson statistics. So this, basically this was meant to introduce the notion of correlation function. I did it with two particles, and we did it using finite solid angle. But the notion of correlation function doesn't itself, it's not an experimental quantity, it's also generally a theoretical quantity that you can calculate in theory, and in theoretical calculation you would not be bothered with solid angles, you would just do densities. That's the first point. The second point is when you never look in sixth dimension in practice, you would always marginalize against a set of several variables. So now we can introduce formally correlation function, not just for two, but for more particle than just two. Okay? And as we do this, we'll discover that there are different quantities of interest, densities, number densities, factorial moments, cumulants. Before I get to that point, I would like to stress that correlations are of interest because they are driven or influenced by two things. They are influenced by conservation laws. So if momentum is conserved, in case in point, if you're emitting one particle this way with a very large momentum away from the beam axis, there must be another particle emitted this way to compensate and to conserve the momentum. So certainly, momentum conservation will lead to strong correlation. Likewise, if you have energy being emitted in some direction, you will also have to have energy emitted in the other direction. Again, energy conservation will lead to correlations of its own. Quantum numbers will also lead, conservation of quantum numbers will also lead to correlation. Obviously, and particularly at the Large Hadron Collider, in the so-called central rapidity of the Large Hadron Collider, in the acceptance that we measured with the ALICE and CMS and ATLAS experiment, we are seeing approximately equal number of positive and negative charges. So what happens in these collisions is that you have one nucleus, Lorentz contracted, hitting another nucleus, also Lorentz contracted, viewed in the lab frame, and so we have some overlap, and this overlap will then lead to particle production. In this overlap now, the number of particles that is produced is very, very large, and much larger, in fact, than the number of protons and neutrons that are coming in, first of all. Second, these protons and neutrons that are coming in are at such high rapidity that even if they interact with other protons and neutrons, they only lose a small fraction of the rapidity they came in with, and consequently, these protons and neutrons are essentially going down the pipe. They're either going down the pipe this way or that way. And so what is left and emitted in the acceptance of the detector, let's say ALICE, are particles that have been created by the collision, by and large. So particles created in the collisions have now to obey quantum number conservation. So that means if you make one positive particle, you have to make one negative particle. And so it means that if you have emitted a plus this way, there has to be a minus somewhere else. Likewise, if you produce a strange quark one way, somewhere else, and I'm not saying it has to be back to back, but somewhere else there has to be an anti-quark, and so on. So charge, strangeness, and baryon number have to be conserved, and by the very fact of being conserved, that will create correlation between particles. There are also correlations that emerge based on the geometry of the collision. And I mean this in a very loose sense. If you have a rho meson, and I'll give you an example of that in a moment, a rho meson likes to decay into two pions. So this decay is happening at finite velocity, so that has a geometry that will create correlation between the two pions that the rho decays into. Jet fragmentation, that I have illustrated here, has a geometry of its own, and that will also lead to correlations. If you have a system that is opaque, like the quark-gluon plasma, then there will be also some correlation that will be induced by the presence of the opaque system. And finally, the presence of pressure gradients, so the fact that I have created, so this is a system surrounded by vacuum, I have now brought in TeVs of energy at Large Hadron Collider. This TeV of energy is now, part of this is consumed into this fireball. This fireball has enormous energy density, and consequently there's enormous pressure, since the system is spatially anisotropic, there is a gradient of pressure, and the gradient of pressure is obviously larger in the small, along the small axis than it is along the long axis, and so consequently the gradient of pressure will push particle more in this plane, the plane of the collision, than out of the plane. So these are the type of correlation one can think of. There are others, but that's the basis for what we can look for. So let me give you some very specific example of how these correlations can occur. I mentioned a moment ago a rho decay. So a rho meson likes to decay into a pi plus and a pi minus. And so if the rho is at rest, angular momentum conservation dictates that one pion will go in one direction, the other pion will go in the other direction. That axis is, of course, completely arbitrary, but they have to be back to back. And so that's what is illustrated here. Now imagine that this row is itself in motion. If it's in slow motion, then its motion will mean that the pions will be deflected in the lab frame. And so there will be some large angle, but not pi. Imagine that this row now is at large momentum, large velocity compared to this speed of light. Then, as it decays, the two pions will be produced near one another. And that's kind of configuration you will see. And so when we measure correlations, we can have this configuration, that configuration at low temperature, and that configuration as well when particles are somehow pushed out as the system expands. Of course, you don't have only two particle correlation, you can have three particle correlation. There are some particles that decay into three particles. There are some clusters that decay into three particles, and that would give you this kind of correlation at rest, which, if boosted, might look like this. And I've already mentioned jets, like these. Jets are partons that fragment, and as they fragment, they can produce 2, 3, 4, 5, 6 particles. Jets at LHC can produce actually all the way up to 50 particles sometimes. And so you have a bunch of particles that are emitted in somewhat small cones, so they're all correlated spatially with one another. To give you an example of how this looks like in practice. And so this is simple Monte Carlo studies I did, plot for the book. And so if you have back-to-back emission or just a small velocity, you have the strand of the correlation function on the vertical axis plotted as a function of delta phi. Delta phi now has a peak, the correlation function has a peak at pi corresponding to back-to-back emission. And this peak has a finite width because in this simulation there was a little bit of velocity imparted to the row. Okay. Let's forget about this one. In this simulation here, I produced the row at very high velocity on average, and what you find is that the peak is gone because now the row is decayed, and as it decayed in motion, the pions that it produced were then focused kinematically onto to be near one another. So in delta phi, they became close to one another. And now, of course, when you put the superposition of decay nearly at rest and at high and slow motion and in high velocity motion, then you can have something that is arbitrarily complicated. Obviously, something that looks like this would have to be discriminated against something that looks like a diagram. So that's one illustration of the type of correlation that we can look for. Another type of correlation that we can look for is illustrated like this. I've already mentioned a little bit. So I have the two incoming nuclei, Lorentz contracted by a factor of gamma, gamma being of order 2000 at the LHC. In the transverse plane, you have one nucleus coming out, one nucleus coming in the page, and then you have this region of darker gray corresponding to the overlap. So that's what I focus on here. And as I've already stated, you have an enormous energy density in here. Consequently, you'll have enormous pressure if there's enough time to equilibrate. This pressure will lead to pressure, there will be a pressure gradient, and obviously the dimension of the system being smaller along the x-axis than along the y-axis, it will lead to a larger gradient along the x-axis than the y, and so this will lead to anisotropy of momentum emission. And so I have here a simple simulation of that, where again I'm showing the correlation function. The correlation function here is normalized, but it's nonetheless the same, basically the same idea. And what you find is that particles are emitted by this system. They're emitted along the x-axis, which which correspond to 0 here, or they emitted along the vertical axis, which corresponds to 90, this here, and then pi, which corresponds to this point here. And so in the type of expansion that we're dealing with here produces a modulation like this. It's a delta phi modulation, as we like to call it. And in this case, the way I generated the modulation is to have only a second harmonic. But in principle, we can have more harmonics. And in fact, this here shows actual Alice data when taken in lead-lead collision with a 1% collision centrality trigger, and when we can see not only a second order modulation, but also a third order. And so the combination of this third order and the first lead to a correlation that has a dip on the OA side. So measuring correlations like this then can tell us a little bit about the expansion of the system and how the system physically behaves after the initial conditions. So let's talk then, generally speaking, about correlation functions. To do that, we need to introduce the concept of number densities, or just cross-sections normalized by differential cross-section normalized by the total inelastic cross-section. And so the notion of single particle density is the differential cross-section divided by the total cross-section, total inelastic. This is for one particle, this is for two particle, and then you can do this obviously for 3, 4, 5, and so on. So these leads to 1, 2, 3 n particle densities. Experimentally, to measure such things, we have to use finite solid angles, so we are going to integrate over some volume, and the volume that we integrate is a matter of choice. When we integrate, we're going to see some number of particles on average. If now I look at pairs in a similar solid angle, the same solid angle, now what I will see is the number of pairs, the average number of pairs. Now there's a little bit of a subtlety here. When you look at pairs, if I have only two particles, 1 and 2, that's one pair, but 2 and 1 is also a pair. So we count actually both. So that's why we have n times n minus 1. Likewise, now if I consider 3 particle emission, n particle emission, the integration over this solid angle will give me the number of triplets or the number of n-tuplets. So if I make this solid angle very large, let's say I would make this solid angle to cover the entire acceptance of the Alice detector, then I would have a measurement of how the number of particles actually can fluctuate, and I'll come back to that. These quantities then are called factorial moments. Okay, so this is first order, second order, third, and nth order factorial moments. For convenience, as an aside also, I can think of these densities in terms of multiplicity on the one hand and the distribution through space on the other hand. And so I can factorize the densities in terms of, so n particle density, I can always factorize in terms of n factorial moment and a probability density in n-dimension space, or 3n dimension space. Okay? There's a certain advantage of thinking that way sometimes to understand the distinct roles of multiplicity fluctuation and spatial or momentum correlation. So this part will capture momentum correlation, whereas this part will capture multiplicity fluctuations. Our reference, or baseline, will always be independent particle emission. That is, you are producing 2, 3, 4, 5 particles. If they are emitted independently of one another, that is, if they are statistically independent of one another, you will always be able to express the two-particle density as a product of single-particle densities. So this is the case of 2. Obviously, it would be the same. It would look the same for 3. You would have rho 1, rho 1, rho 1, and so on and so forth. Which is what I have here. For n particles, you would have rho 1, n times 2. So, uncorrelated particle emission or independent particle emission is boring. It's not very interesting. I mean, certainly we discovered jet punching because we were not looking at independent particle. They were highly correlated. But so we want to what we're interested in is looking at what is the structure of these correlations. Okay. The causes of correlations can be many. I mentioned a few: energy momentum, quantum number, and so on, geometry. So all these different sources of correlation will act differently on the particle correlation that we try to observe. And so what we're going to do here is to try to characterize the correlation based on their source of correlation. And so there are processes that will lead to no correlation whatsoever. There are processes that will lead perhaps to only 2 particles being correlated, perhaps 3, perhaps 4, and so on. So in general, I can think of processes that would produce n particles being correlated. So I will use this notation to denote that I have a process that produces n particles, and all of these n particles are assumed to be correlated by the very nature of the process that produce them. Now, if I'm observing n, not m, but n particle, n being larger than m, it means that some of these particles may be correlated and some will be uncorrelated. And so as I look at n particle densities, some fraction will be associated with correlated production and some fraction will be uncorrelated. So what we would like to do is to grasp or determine what fraction is actually correlated emission. And so there's a plurality of processes that can cause this, these correlations. We want to be able to extract them. So we're going to introduce the notion of cumulants to do this. Now, to do this in the right fashion, we would use generating functions. But I'm not going to do that. I'm going to focus on the physics more than the mathematics, or try to. So what I will call a cumulant of order m will correspond to a density, or a experimentally that will be an estimator of the density. And in the literature, you will often see rho with a hat. The hat doesn't mean estimator, but it means cumulant. For whatever reason, people have liked this notation. But you also see C for cumulant or correlator in the literature. So in here, in this presentation, I will use C to denote cumulant. And what I mean by cumulant is a density of particle involving n particle, all of them being correlated with one another. And so now I'm going to look at a system of n particles, n being in principle larger than m, and I'm going to try to break down how these n particles can be correlated. So if I give you n particles, there are many ways to pair them. There are many ways to put them in triplets, quadruplets, and so on. And so this is called partitions of n particles. Right? There are many ways to partition n object into n subgroups. So I'm going to use the term n cluster to denote objects that are correlated involving n correlated particles. And so what we need to do then is to find all ways to produce all permutations, so to speak, of making these n clusters part of a collection of n particles. So there's several ways of doing this. One easy way to visualize this is to use this notation, this graphical notation. So this corresponds to densities on the left side, and on the right hand side of the equality I have cumulants. So obviously if I look at only one particle, I can't tell whether this particle is correlated to another, so that becomes a trivial C1 cumulant. If I'm looking at two particles, these two particles could be completely uncorrelated. That's what I symbolize by adding these two circles. Or they can be correlated with one another. That's what I'm going to write like this. So this will correspond to the product of two cumulants, C1, C1, and this will be a true two-particle cumulant. Going to a collection of n particles, three particles, I can have three independent particles being produced. I could have particle 1 and 2 correlated but independently of 3. I could have 1 and 3 correlated but independent of 2, and likewise 2 and 3 correlated but independent of 1, or all three could be correlated. Moving up to 4 particles, you can repeat this logic and see that it becomes a little bit more complicated. 4 uncorrelated, 2 in 1, 1, 2 in 1, 1, but there are different permutations of doing 2 in 1, 1. And then you have 2 correlated, but you can pair them differently. That's what you have here. And then you have 3 in 1, but you again have different ways of doing this, 4 ways. And then at the end, you have all of them being correlated. And so when we measure densities, we have the possibility of having all these combinations of correlations. And so what we want to do experimentally what we do, we measure a number of particles. That can be a number of singles, pairs, triplet, quadruplet, and so on. And from that, we wish to extract the cumulants themselves. So we need to, so to speak, invert this graph to obtain the cumulants experimentally. So at the first particle level, it's trivial. Right? Rho 1 equals C1. The density is the first cumulant. The signal particle density is going to be C1 of the first, C1 of the second, and this correlator of the 1 and 2. And so now you can tell that to extract this quantity, I'll just have to subtract the density by this product. For 3-particle density, I will likewise now have a 3-particle density that will be a product of singles, a pair and single, pair and single, pair and single, and triplets. So now to get this cumulant, I will need to measure the density and subtract all of this. I don't need to do this for, I think you get the idea for densities. In principle, I can do this for even higher densities. And now, to this day, CMS, Alice, and Atlas have gone up to measuring 8 particle, even 10 particle cumulants. So you can imagine the mess of terms that you have to look at. So on the theory side, you are able to calculate these cumulants. On the experimental side, we measure densities. So somehow we have to connect the theoretical objects to the measured objects. So we're going to, from the experimental perspective, we're going to try to extract cumulants out of the densities that we've measured. And as I said, I already alluded to, we're going to invert the relationship that we have. So rho 2 being equal to a sum of C1, C1 plus C2, we just bring C1, C1 on the other side. And so that becomes C2 being the difference between the pair density and the product of single particle densities. This is for 2 cumulant, 3 cumulant is shown here. So I just, I've rewritten the density, and then you just move things over on the left-hand side, and at the end of the day, you get this expression here. So you have a term, the 3-particle cumulant will depend on the 3-particle density, and then combinations of 2 and 1, and then a trivial term of product of singles. The algebra is such that when we do this, you end up with minus signs here, and a +2 sign, +2 factor here. So that's the logic of doing these correlation functions. Now, before I go any further, I should stress that when you do this, you are going to measure positive definite quantities for each of row 3, row 2, and row 1. But when you start doing this kind of mathematical contractions, there's a possibility that this will be larger than that, and you'll end up with negative numbers. So these correlation can be negative, just like a covariance can be negative. That's the first point. The second point is that these numbers will be typically large. These numbers will also be typically large. And so when you subtract 2 large numbers and the end product is small, you will have possibly a very large error on the difference. So even though you may have very good statistics, very good precision in measuring row 3, when you measure C3, you will have to have even better statistics because now you're dealing with a quantity which can be very small compared to row 3. So experimentally, that's the challenge. The challenge becomes exacerbated when you go to 4, 5, 6, and so on. Particle cumulant. So you need extremely large data sets to do this kind of analysis, especially if you want to go all the way to 8 particle cumulants. Schematically, I can write this way, just as a visual aid. This is 2nd cumulant, so apologize. And so 3rd cumulant, 4th cumulant, and so on. So just to illustrate the challenge, the experimental challenge of doing this. Okay. All right. So this is the definition of cumulants. Now let's try to think about these cumulants and how they behave in finite systems, in collisions. And so to do this now, we have to, in particular in the context of heavy ions, we have to look at collisions, and collisions that vary in centrality. Right? So here I have my orange spectacles nuclei, they collide, they produce a bunch of particles, and based on the number of particles that were produced, now I can estimate the collision centrality. And so when I do this, then I will have large multiplicities. These large multiplicities then can be broken down into clusters of n cumulants. For the purpose of my discussion, I will make a simple approximation. I will say that these collisions consist of a superposition of independent processes, and that could be independent nucleon-nucleon collisions or quark-quark collisions, or they could be a superposition of identical systems, whatever these systems might be. And I will use this then as a baseline to understand how these cumulants are going to behave or scale with collision centrality. So this is my setup. I'm saying here I have a certain overlap between the 2 nuclei, and the number of participants will determine how many particles are produced, but it will also determine how many correlation sources are present in the system. So I have a collision of centrality. I'm going to try to compare to what I would see in PP collisions. Right? And so the cumulants in PP collisions I'm going to call C subindex n with a label PP to denote that they're from PP. And I'm going to be interested in measuring these cumulants in AA collisions, or goal, or whatever. And so what I'm interested in now is trying to relate these cumulants in AA collisions to those that would be measured in PP if nothing whatsoever interesting was happening. So, if I have an independent collision system with m sources, then the number of n cumulants that I would see in AA would be the cumulants that I see in PP, but I have a system consisting of n such sources. So what I would see in AA would be just n time, the number of sources producing n particles. So that would be just how the cumulant in AA is related to that one, the one in PP. Okay? This n, just the number of sources, the number of such correlated sources. Of course, in any collisions from one collision to another, there will be fluctuation in the number of such sources. So at the end of the day, when I see experimentally, it has to involve an average number. Okay? So if there was nothing interesting happening in these collisions, no QGP, no collectivity, nothing whatsoever, I would see that the cumulants that I find in AA collisions would be strictly related with the factor of n, the average number of sources. So, what that means in practice is that whether I look at densities, the densities in AA collisions relative to those in PP, they are related by this factor of n. If I integrate over a large solenoid, I'm measuring multiplicities, then the multiplicities in AA would be just this factor n times the multiplicity in PP. And likewise, the cumulants would be given by this expression as well. Now, for densities larger than 1, I will have a slightly different situation. If I'm now looking at the number of pairs in AA collisions, there are many ways of observing pairs. So, when I do this in PP, I'm going to observe some number of pairs, but the number of pairs I will see in AA will certainly be a factor larger than this. It will be the number of such PP collisions there are in the one AA collision I'm looking at. And so, this will be the correlations seen in PP, and I will have a strength equal to n times that in AA. What complicates the matter here is that when I look at pairs, I can see one particle from one source and another particle from another source. Right? These being uncorrelated, this factorial moment then factorizes and it gives me a square of the number of particles in PP. How many ways how many ways can I generate this pair? Well, I have n sources, so I can combine n sources with n minus 1 sources, so that gives me n times n minus 1 sources. Okay, so that then gives me is what we call a combinatorial background for the true correlations. Okay, and so I express this now in terms of densities as well. And so we have C1, C1, C2 in AA. I express these in PP, so I have C1 times MS, I have that square. And here I have C2 in PP times MS, corresponding to C2 in AA. I do the algebra, at the end of the day, what I find is this term, which is what we call the combinatorial terms, right? And then I have a second term, which is the true correlation that we've seen in PP. So this is what I get from the density. If I do this with n particles, I get something similar. And so if I'm looking at n particle densities, I would have likewise combinatorics of single, combinatorics of pairs and singles, and so on and so forth. So that becomes quite complicated. So at the end of the day, for instance, single three particle densities in AA would be related to three particle densities in PP in this fashion. And so you have this term here, which is purely combinatorial with an n to the power of 3. And you have this term, which is the true three particle density with a power multiplied by n to the power 1. So obviously, experimentally, if n is large, because you're dealing with large nuclei, central collisions, then this term will de facto dominate over this term. And so what you're trying to measure maybe is how these three particle correlations are evolving with centrality going from PP to central AA collisions. But what you see is dominated by this combinatoric term. And that's why we like cumulants, because when you measure cumulants, you will see that we can focus after doing the algebra, we can focus on this one. Experimentally, it's interesting and advantageous to also look at normalized quantities. For instance, we can look at what I call little r here, the ratio of n particle density over the product of single particle density. So this is an n density, so I have n times the single particle here. The advantage of doing this sort of normalization is that if there are efficiency losses in the measurement, that is, if I'm losing pairs because I'm losing because of the detection process, I will lose pairs, and the efficiency will cancel. The efficiency will play out equally in the numerator and the denominator, and so this quantity will be essentially robust or independent, if you will, of the detection process. This second quantity, with a capital R, is what we've used recently in the literature to talk about the cumulants divided by the product of singles. Oh, thank you, sir. All right. So these quantities are now basically the ones that are measured in RIC and LHC experiments. Just as an aside, if I can do this with densities, but I also can do it with factorial moments in the same idea. So this relieves to normalized factorial moments. And so because people are increasingly measuring factorial moments, then it's interesting to look at how these scale. So it's, having done what we've done so far, it becomes trivial. The factorial moment, normalized factorial moment, the normalized cumulant, R sub n, is just being given by this expression, so that you have a scaling by 1 over n to the power n minus 1. So that's going to be so two particle cumulant, that's going to be 1 over n. And so this phenomenon of scaling down by 1 over n to the power some n minus 1 is what we refer as dilution of the correlation function. And so just to reemphasize the point, when you normalize the cumulants in this fashion, you have a dilution by the power of the cumulant, and that comes from, this dilution comes from the time when you're looking at correlated pairs. There's also a combinatorial background coming from uncorrelated pairs. So if you're looking at all the particles coming from one source, it's great, but when you look at, let's say, 4 particles, obviously from this example you can have 2 from one source, but 1 from 2 other sources. So let me now give you some examples of correlations that have been measured by people. So here's an example of net charge correlations. it was proposed already in 2000 that one way to identify the presence of the QGP would be to measure net charge fluctuations. So the net charge, you take the number of pluses and minus the number of minuses, that you call that the charge of the event in some acceptance, and that will be now computed relative to the total number of charges in the event. And so then people constructed what they call the reduced variance. So taking the average of delta Q squared becomes the variance of the quantity, because on average the mean of this is essentially 0. And so by people were saying by measuring this we would have access to evidence that we had formed the quark-gluon plasma. The logic was that in hadron systems you're dealing with charges of +1, -1, whereas in the quark-gluon plasma you're dealing with charges of 1/3 or 2/3. And so if you then translate charges in terms of 1/3 and 2/3, you find that whatever fluctuations you might have, when you go from +1, ±1 to ±1/3, ±2/3, these fluctuations would be consequently reduced. And there were tens of papers written on the subject alleging that this would be a fantastic observable to seek evidence of the formation of the quark-gluon plasma. In practice, there were two schools of thought. One was to measure this directly, one was to measure this quantity here, and I apologize for we're using R, but this was the notation that was used in the original paper. So R being the ratio of the number of pluses to the number of minuses, and taking the variance of this ratio was multiplying with the multiplicity. Volker Koch and collaborators called this D, and they made prediction for what D should look like. And there was very different values for hadronic matter and quark-gluon plasma matter. And so this was deemed to be a very interesting observable to identify the formation of the quark-gluon plasma. And so the predictions are shown here for in terms of omega, in terms of D. And so if you have Poisson emission, this variable will be 1. If you have a hadron gas, the value of this was predicted to be 0.7. And if instead you have a thermalized QGP, just by virtue of going from ±1 to ±1/3, 2/3, this would be very much suppressed. In terms of the quantity D, these were the values. What I did and what other people did was to measure a different quantity in new dynamic that I will describe in a moment. And in terms of this quantity, again, there were very different values of seeing this. So let me skip to the results. So that got people somewhat excited. So what we have here is this quantity, new dynamic. New dynamic was introduced, maybe I can justify it a little better. Can I justify it a little better? Not really. What I did, let me try. So, what I said is I have a ratio of the number of pluses to the number of minuses. I can look at the average value plus some fluctuations. When I propagate all of this, calculate the variance of this ratio, going to the punchline and looking at the dispersion of variance of this ratio divided by the value of the ratio itself, I get this expression. And so this expression is specifically what we call new dynamic. And so this would be done for plus pair, minus pairs, plus pairs. And so we endeavor then to measure this kind of quantity. And the idea, as I said already, was that we were expecting very different numbers or values depending on what kind of system was produced. And so this is the kind of thing that we saw. This is the magnitude of the observable. This is the number of particles produced, and you see a 1 over n behavior. Okay? And what to get rid of this 1 over n behavior, this 1 over n behavior is what I talked about a moment ago, what I call the dilution. And so to get rid of this dilution phenomenon, we multiply by the multiplicity. So I have the multiplicity times the dynamic, and here what you see is that it's essentially flat, or it increases or becomes a little more negative going to more central collisions. What was very confusing at the time was that this was in line with what was expected with resonances, and whereas the quark plasma was actually down below here. So we were happy to see correlations, but we were unhappy that we didn't see actual suppression of these correlations to the extent that was anticipated. It turns out that this was doomed from the start. Charge conservation plays an important role here. But let's move on. There are other types of correlation that people have looked at or are interested in looking at. There were discussions already in the 90s for looking at temperature fluctuations. The temperature fluctuations are of interest because they can tell us in principle about the heat capacity of the medium. There were also fluctuations of multiplicity that were predicted and to be a measure of the compressibility of the system. So in the 90s and early 2000, people were really interested in measuring fluctuations of observable, like the multiplicity, the charge, and also the temperature. I personally got interested in measuring the temperature fluctuations. Unfortunately, that's a little difficult, so you can't measure the temperature of one single event, or at least that's difficult. So we decided to use a proxy, which is the PT of the particles in the event. And so if the temperature of an event is changing, you would expect that the PT of the particles in the event is increasing or decreasing, even if they're fluctuating. So we set up to look at this sort of thing. And the idea is that you have a collision. The collision injects heat into the system. The injection of heat must translate into an increase of temperature. And if you have fluctuation in the heat transfer or the heat injection into the system, depending on what the heat capacity of the system is, you could see different types of fluctuations. So that was one of the points of interest. Mathematically, you can see this like this, where you have the heat being injected into a system causing a temperature increase or decrease, that would depend on the amount of matter that is in the system and the heat capacity, the specific heat of that at constant volume of this matter. And so you can do it at constant volume, constant pressure, but the idea is the same. You have a relation between the heat and the amount of and the temperature in the system. So there were then predictions that there would be fluctuations that would be determined by this kind of quantity. So this is the probability of producing a particle at a certain temperature. And then this tells us that there will be fluctuation in terms of delta T, fluctuation in the temperature. And there were very prestigious people that mentioned this. In practice, the way to access these fluctuations experimentally was to measure the dispersion of the temperature, the variation of temperature relative to the mean temperature, and that should have been telling us, or should be telling us, about the heat capacity of the medium. And so this is something that we've pursued and are still pursuing, but we have nobody has achieved that yet. But the idea is that experimentally what you should see is that if there are fluctuations in the temperature, the spectrum of the particles that are produced should have a slope that varies from one event to another, and getting access to the slope, which should tell us something about the fluctuations in the temperature. In practice, that's rather than measuring the temperature, we decided to measure the PT, and cutting to the chase, we started to look at, because I'm going to run out of time, we started to look at momentum fluctuations. And this is an example of how momentum can fluctuate, the average momentum of particles can fluctuate, and we were looking at how such fluctuations deviate from what you would expect if there were no correlation whatsoever. And so that was an example. In practice, we ended up not liking this particular way of doing the business, so we introduced momentum fluctuations and momentum correlators. And so the momentum correlation, so what we would do is on each event, we would sum the momentum of all the particles of the event, particles of interest, and we would then look at the average of this quantity over an event ensemble. So we would divide out the number of particles in the event, that gives us the average PT in the event, and then we would divide out the number of events, and that would give us the average PT. I can do this with, so this is with single particle, I can do this with pairs, and so now with pairs I have, for each particle pair, I have the deviation from the mean, the product of the deviation from the mean, and I can then look at how this averages over an ensemble event, and we work then, we get this type of, let's see, we get this expression here. So what we call delta PT is the average of this sum divided by the average number of pairs, and we were hoping this would tell us about the heat capacity of the system. Unfortunately, it turned out to be, and if I can cut to the chase here, it turned out to be complicated. Again, here you have this 1/n behavior, but you also have a scaling that depends on the magnitude of the average PT in the event, and we tried to eliminate this magnitude by dividing by PT, but even by dividing by the PT, you can still see a huge variation with the centrality of the event. Okay, and we have some measurement by Alice also. I wanted to get to two-particle correlation, but I think I'm running out of time already. And we have measured two-particle correlations in the lead, so this is the type of correlation that we did with the former postdoc, and so in lead collisions at 2.76, we measured this two-particle cumulant as a function of delta phi and delta eta in these cell structures like this. And I will just say, and I will stop in a moment. I just want to emphasize that I spent all this time to tell you about the scaling of these correlators, and the punchline is here. If you have lead-lead collisions or gold-gold collisions being just a scale version of PP, so here I have the correlator in somewhat peripheral collisions. So obviously what you see some modulation in delta phi. You see a very sharp peak at delta phi 0 either side. And so if global collisions were essentially the same as PP collisions, even in central global, what you would see is just this shape, but shrunk by 1/m. Right? So this should shrink as 1/m as we increase the number of participants or the number of correlated sources. What we see in practice is this huge modulation appearing, which I've talked about, which corresponding to, this is a cosine 2 phi, that corresponds to the emergence of flow. I've already told you that this comes from this pressure gradient, and then, so obviously there's this enormous departure from the 1/m scaling. You can still see a little peak here, but that peak becomes extremely deformed in the most central collisions. And this really looks nothing like that. And so it's clear that in lead-lead collisions, and shown here, you have a complete departure from PP. So even if you were doubting that flow measurements would return something about collectivity, just seeing and looking at these correlations, you can tell that the system, whatever the system is, it is very, very different from what it is in PP collisions. And so that was, for me, one very interesting moment that we actually confirmed visually that we were looking at systems that were very different from PP collisions. We can talk about many other types of correlation functions.